Hi everyone, and we covered the fourth question, and now we'll move to the lecture for today. And for today we're covering sorting. So to get started with sorting, so simple definition of sorting is there. Oh, I've heard someone explain it a really good way. When we take an input and then give it some meaningful order. And more informally, for thinking in terms of numbers, then given an array of some size containing numbers, then it's a permutation of those numbers. I think I'm just going over it. Is there anyone who doesn't know what sorting is? Okay, yeah, I think we're good. So the example here is clear. The A was not sorted, then after we sorted, it's B. And then the idea is how can we do it efficiently? And in this lecture, we'll cover some of the more basic ones. And why are we covering this so soon, and why are we covering it as a full lecture? It's useful in many different areas. There are obvious ones, for example, like if you wanted something sorted, then sorting it would be the way to go. Something like that, basically. We'd have questions where simply sorting it would be the answer. We just want to do it efficiently. And also there are problems that becomes easy once we sorted it. For example, finding a median or doing a binary search. They both assume a sorted array or a sorted sequence. So there are non-obvious applications as well for finding duplicates or data compression. And in this lecture, we'll be covering some of the more simple ones. If you're familiar with them, it's bubble sort, then selection sort, then insertion sort, and then counting sort. And I think one of the questions you could have is why would we learn the basics? So if you are familiar with the algorithms, we'll cover them soon. They're the first three at least, bubble, selection, and insertion sort, they're a bit inefficient, and we don't recommend that you use them in practice, in coding or interview preparation. Then why are we learning them? I guess that's a good question to ask. And the ideas that we get from those, the ideas they had when they implemented it, some of the insights they had. Okay, it's from a meeting, someone's joined, and some of the insights that we have from there, they could help us in solving questions, other questions. For example, this question, it's also going to be added in the sheet, and you'll try it also. And what it asks us is, it's a long description, but to put it short, you're given an array of zeros, ones, or twos, but they're not sorted. So we can have something like this. And essentially what we want to do is we want to sort them. Obviously, we can try any algorithm that we have in mind, but the generic algorithms won't give us won't fulfill this condition where we just want to go through this list once, we want to iterate once, and we don't want to use additional memory. And by the end, we want the list to be sorted. So it's a very interesting question. After we've covered this class, it would be on the sheet, it's called sort colors. You should give it a shot, it's a lot of fun. And some of the ideas that we learned here, the ideas they had when they implemented these different sorting algorithms, they can help us here also. And so we can start straightforward with bubble sort. And since we have an example here, we'll run it through this one. The idea that comes with bubble sort is we can go through the list several times, and then whenever we see something that's out of order, which is in the wrong order, we flip them, we swap them basically. And we keep doing this until the array is sorted. And so for this one, let's start with this one removed. It might help a bit. And then, for example, let's start from here, from way over here, and imagine we can actually look at the visualization. It could describe it much clearer than we do, and it starts between the two, and it's trying to sort them in increasing order, so it swaps them. Same with the one, and it keeps going over and over again until we get to the end of one bubble sort, and then it starts over again. And can anyone tell me what we've achieved so far? Is there an element that we're sure is in the right place after we finish one iteration of bubble sorts? Any hands?
The largest one?
So the largest one is taken to the end. Yeah. So essentially we bubble the largest element all the way to the end. So We can keep doing this over and over and over again. The video can continue until we have everything sorted in the right order. And we could suffer through the rest of the animation. Just give it some time, probably end soon. And we could. Oh no, it just goes somewhere else entirely. So I think it's clear. Is there anyone who's a bit fuzzy about the bubble sort algorithm? So any questions on the idea behind bubble sort? So in that case, we can talk about why it's inefficient, why the rest would also be efficient, and with that comes the idea of time complexity. So this is how we measure effectively, how we check how inefficient or how efficient it is, and we do that by measuring the number of operations it takes to complete the task. And for example, for this simple input right here, we'd first start with doing this check and seeing if they're in the right order. So we do this check, and then this again, and then this, and then this, and then this. So for example, here we have an array of 7 elements, and we make 1, 2, 3, 4, 5, 6. We make 6 checks. So imagine we had an array of size n. We had an array of size n. How many checks are we going to do in our first pass? Through n minus 1. Since we're doing 2, 2, 2 at a time. So in our first iteration, we make n minus 1 checks. So these checks, they are considered elementary operations. Something like checking equality, assigning variables, adding other elementary operations like multiplication. And as you're more familiar with your language, you can check what other operations you can consider to be basic cost of 1. Basically, we're counting each check as 1 and adding it up and saying n minus 1. As you get more familiar with the language, you can Google and you can check what the time complexity of each function that your language provides you is. And then afterwards, by the end, we would have checked these 2, then check these 2 again, check these 2, we would have flipped this. Oh, my bad. 1, 0, then flip this again. So we have a 0 here. And then flipped, when 2 comes here, we would have flipped it, and this would have been a 1. Then a flip again, and then finally here we'd have a 2. So afterwards, we're only going to check right up to 2. We don't include 2. So in this case, it's going to be 5. And can we, in terms of n, can we continue? What would be the next iteration?
n minus 2.
N minus 2. And then we keep doing this, n minus 3. And how far does this go? Up to, any hands?
1.
Okay, yeah. It goes right up to 1. And then since we're making each of these checks, we can sum all of them, which is counting the operations in terms of n. In this case, our n, we considered our n to be the input size, the size of the input array. We can define n by every problem. We can see what's relevant. Then we can define our n as such. And then we can calculate the number of operations. And for this case, we have n plus 1 plus n minus 1 plus n minus 2 plus n minus 3, all the way up to 1. Is there anyone who knows a simpler way to rewrite all of this? A single term. Did I hear something? Okay, factorial. We have one option, but this is plus. So factorial wouldn't work. Are there any ideas?
Polynomial. Polynomial.
Polynomial, yeah, but like there'd be like a simple formula. Is there anyone who's familiar?
N
N squared minus n.
over.
Yes, there's an over 2. Or like for people who are more familiar with this, we have.
Yeah.
So this one is the one that's seen here. And so after we have this, basically this counts all of the operations we did, and then we take the biggest power because we're interested in how the function behaves when there are a large set of inputs. We have a larger n. The one that matters most is this term we have right here. So we'll take this one specifically. So we ignore like the constant, which is over 2, and then the subtraction. with the smaller powers. So we ignore all of that and we say this entire algorithm would take off n squared. So basically when we big O of n squared. So basically when we say this, what we mean is as the size of the input grows larger and larger and larger, what matters more is the n squared term, so this becomes more significant. So this is the class of algorithms it's in. And this is part of why we consider this to be inefficient for example, on any of the platforms that you're working on, if we have, for example, 10,000 is the size of your array, then this wouldn't be a suitable solution. It would take in terms of seconds instead of milliseconds, which is not what we want. So that's why we consider this to be inefficient. And there's also the pseudocode for those of you interested. So we go from the first element all the way to the last unsorted element. So in this case it would be from here to here, and then the second step it would be from here to here, since this one is sorted. And then we check if they're in the right order, which is the left element is greater than the right element. So if that's the case, then we need to swap them to maintain the right order. So we keep doing that and doing that. And then once it's sorted, meaning we didn't make any swaps, if we go through the whole thing and we don't make any swaps, that means everything we've seen so far is in the right order. So that happens, we can jump out. And here we can speak in terms of this being a constant time, because if we're doing a check and swapping them, we can do it in the same assignment operations, a bunch of assignment operations. And this is also assignment, so this is considered basically O1. And we do this n times. This will go n times, and this bigger loop out here at the worst case, in worst case being a completely reversed list. So if we had something like 4, 3, 2, 0, we'd have to flip everything over and over and over again. So in that case, we'd have something similar to n right here. So that's why we said n squared for this one. Okay, and in this case, there are some other things we need to consider where we're talking about sorting algorithms. The first one is it in place or not? And this is the simpler one to see. We can check if our algorithms uses any extra space. An in-place sorting algorithm would not require any extra space. And in this case, that's exactly what we're seeing. We just check if they're in the wrong order. If they're not, we're not taking them anywhere else. We're just swapping them right here. So when we say extra space, we don't count the constant space, meaning space that doesn't increase as n increases. So in this case, we keep track of the indexes. So that's additional memory, but we don't consider it because it's only a very small fraction and it doesn't increase as n increases. So that's what we mean by additional memory. So in this case, we can say bubble sort is stable. Bubble sort is an in-place sorting algorithm. And stable, with stable we mean, for example, if we had this array, we see that 8 and 8 are equal. In that case, when we output them, the algorithm might put it like this, or it might flip the two. In both cases, we consider the array to be sorted, so it did its job. But if it's stable, whenever the two elements are equal, it places the one that came first, and the one that came next. And for example, if we're considering numbers, 8 is equal to 8, 8 is equal to 8, we wouldn't care. But for example, if we're thinking in terms of classes that have, and we're trying to sort them by a certain attribute, and for example, if that was age, and if we have these ages, and we can be worried about the ordering of people who have similar ages, and so that's why we're concerned with whether or not a sorting algorithm is stable. Is everyone clear with what stable means? Are there any questions? So, let's see if I can. Is bubble sort stable or not? Any takers?
It's not.
Why is it not stable?
Maybe it depends on the implementation.
Yeah, can we implement it to make it stable? I think that would be the better question to ask. Can we implement bubble sort so it can be stable? Okay, Benassi, what do you think?
Yes, you can.
Okay, I saw you nodding, that's why I asked. And yeah, we can. So we can do the check. So for whenever two elements side by side are equal, don't swap them. If we do that, that means we assume that this is the right order and we continue on. So in that case, if we handle that case, we only swap when they're explicitly in the wrong order. That means when we continue on, it would be a stable sorting. So another simple sorting algorithm. Oh, by the way, are there any questions regarding in place, time complexity, stable? There you go.
What is the application of a stable sorting?
Okay.
How do we benefit it?
For example, there are, like, for example, if you need it for a specific application, but even other than that, there's an advanced, on the next lecture, we'd cover radix sorts, in which, like, it's some alteration on a sort, and it assumes that your sorting is stable. So, for example, for those, there are some problems that it would require the sorting to be stable. And for example, just to run it through, we'll cover it later, but if we had 382, 381, 287, and radix sort would sort by the digits first, by the 10th place first, then by the 100th place, and then by the 1000th place, and it continues on doing so. And we'll cover it later, but for this algorithm, for example, it requires the sorting to be stable. So there are problems that might require that. That's why it's a property that we check.
Maybe in real life, so you and I go somewhere and then we put our names, and let's say we have the same name, and then you come in before me though, and then I come after you, and then those people, you should have priority, but we have the same names, and if they do some sort of sorting, they should keep you first in that list. So they should keep in mind that you came in first, even though we have the same names, and they sort our name, they sort the list by our names. So something in real life could be similar to that.
So, yeah. Are there any other questions regarding bubble sort in general? Okay. In that case, we can move on to selection sort. And what it does here is, it's simple. And the idea is whenever we get to an index, starting from here, we try to find what element we should put here. What's the right element to put here? And so if we start from the one right here, which element should be placed here? The one that's minimum or the one that's maximum? If we're sorting it in increasing order. Minimum. So by the time we put it here, we can check the entire array to find the minimum element, then place it here. How about when we get here? What do we want to place here?
Second minimum.
Second minimum. How do we get the second minimum? Sounds like a tough one. Exactly. We don't include this one. Rather, we go through this one instead because we know the minimum is here. We again find the minimum value we can. Then we keep doing that over and over and over again until we get here and we have only one element here. So we put it there and then we continue. So we can quickly see the some parts of the visualization for this one. It's, I think, a similar example. And then it goes through the entire array first, trying to find the minimum. Until now it's 1. And whenever it finds another repeating element, it just leaves it. And then again it goes for the second minimum it can find, in this case 1 again. And then it goes, and it keeps doing that. Are there any questions regarding the general idea behind selection sort? Okay, in that case we could jump into some of the properties. Can anyone tell me what the time complexity is?
And scaling?
Oh, okay, yeah. Why would it n squared?
Like because in each step, like first we start with the n, then n minus 1, n minus 2, n minus 3. It was very similar to the previous one that we saw.
Thank you. Yeah, it goes as we did last time. We go through the entire list first, and then second time we go the entire list minus 1, the entire list minus 2. We keep doing that until we get here. So by the previous idea we had, we see that this is also of n squared. And the other question is it in place? Do we use any additional memory?
Yes.
Okay, so it's in place.
Yes.
Yes. In place, it is yes. And how about stability?
Yeah, wait.
I meant to say no.
Yes.
Oh, okay, so it's not
I
in
got
place.
confused, yeah.
Okay.
Yeah, we use of course extra memory, but since it's constant, that's why.
Okay, so you meant to say that this is not in place?
Yeah,
Okay, my bad.
I bet.
So why do you think it's not in place?
Maybe we are keeping track of. Oh, my bad. So in place meant that we are not using extra memory, right?
Yeah.
Okay. What if I am using extra memory here?
How would the algorithm use extra memory?
Well, it's keeping track of the minimum scene and the minimum position scene.
Yes, it's keeping track of the minimum scene and the minimum position
Right.
scene, which are two numbers, right?
Right.
And with whatever the size of n, those two numbers won't change. Like it won't be like 5 and then 10. It'll still be those two numbers. And that's why we say it's not any additional memory, it's constant memory. So that's why it's actually in place. And how about from something else? Is it a stable sort? Any hands?
I think it is.
Okay, could you tell me?
As we see from the algorithm,
Uh-huh.
I mean visualization, like since we, like if there is let's say 2, 1, since we get the first one firstly, then we just skip the other one,
Yeah,
then we just keep going that. That's
Okay.
why I think it looks stable.
stable. Okay, are there anyone who disagrees with them? Anyone who thinks it's not stable? Okay, we could. If there's anyone who I think Sain's writing something. If there's anyone who can come up with a counterexample, so situation where you can write it. Situation where it's not stable, then it could work. It's not stable, then spoil that for you. If anyone can come up with like an example to show that it's not stable, that'll be awesome. You can consider like a small break and just think of an example and input. Oh wow, that was quick.
Why it's not stable, right?
It's not stable. Yeah, why is it?
I think if, for example, in this case we have 2 1s,
Mm-hmm.
both are the minimum. So we'd store the first one, but then it would continue scanning or checking, and then when it gets to the second one, it would replace the first one.
Oh, actually, that's not how it goes. First, it's gonna take a while. First, it goes and finds the first one, then places it at the.
It would register it as the minimum, and then it would continue. But I think it would replace the minimum because it is now found.
Yeah, and then it switches it with 14, not with 1.
No, it's not switching. It's keeping count of the minimum, right?
Yeah, it goes on and finds the minimum.
Yes, and when it finds one, it would still keep going, right?
Yeah.
To check if there's anything
smaller.
And if it finds one again, wouldn't it replace the first
Oh.
one?
No, it won't. Because you can implement it so that it doesn't, and that's how it was implemented. So that if we go a few seconds back, after it found this one, it goes, and then it just jumps that one if it's equal. So, yeah, it's not stable, but anyone who can show me a simple example of why it's a situation where it's not stable.
Do we have hints?
Yeah, okay. We can imagine where we'd have to swap something and then it could go way back. Anyone thought of any example? It could be from you guys as well. Oh, okay.
For example, if you have 3 1s and it makes the initial one go way further.
Okay, yeah. Could you write up an example or? Okay. You can simply show it. For example, if we had this 2 and then this 2 again, and then we had a 1 or 0, anything. First finds the minimum, which is 1. It swaps those 2 out, so we have a 1, and I think it's good. A 2, and then another 2. So it finds the second minimum. It lands on this one, puts it here, and this would be the end of it. And we started here, but we ended up here. And this is the situation that it's not stable for this type of example. So this is why we say it's not a stable sorting. And I think, let me go ahead and check, yeah. So there are 2 more remaining, and those will be presented by Beimnet. So welcome him with warm applause.
So we covered the first two of the basic sorting algorithm, and I'll try to explain the last two. So here it says insertion sort, and in insertion sort we'll try to sort the beginning of the list, and whenever we find a new element, we'll try to find the correct position of that element in the sorted part of the list, and we'll try to insert it in that position. In an example. So if we have, for example, 5, 3, 1. So initially we put a marker on just after the first element. What this tells us is this part of the array is sorted, since it's only have one element, it is sorted right, and the other part of the array is untouched. We haven't seen it. It may be sorted or not. So what we do each time is we take out one element from the untouched part. We take out 3, and we take we will try to find the correct position of 3 in the sorted part of the array. To do that, we take out 3 and compare it with 5. That is, 5 is greater than 3. So we move 5 one to the right, and we place 3 here. And now we have 2 elements in the sorted part of our list. So we move our marker 1 to the right. We do the same for 2. We take out 2. We take out 2, and we compare 2 to 5. 5 is greater than 2. So we shift 5 one to the right. We compare 2 to 3. 3 is greater, so we again shift 3 to 1 to the right, and we place 2 here. And we move our marker 1 to the right, and we do the same for until all elements are sorted. Is it clear, right? Yeah. There is a visualization on the next slide. It's starting from the second element. Finding the correct place for the current element and putting it in the correct position. Yeah. So, yeah. Any questions till now? Okay, so to do some analysis on the time complexity and other properties, time complexity would be n square. For the same reason, selection sort and bubble sorts are n square. But one other way to know if a certain algorithm is n square, if it's not purely n square, meaning for every element, if we are not searching all the elements in the array, we can think of an average. For example, we are doing we are trying to find the correct position for every element, right? But for 3, we only have to switch 3 one time. For 3, it is one time. For 5, in worst case, let's see it in example. I'm just trying to show you another way of knowing that is n square. In worst case, let the input be reversed. So we start from here, and we swap 4 one time, 3 2 times, and 2 3 times, and 1 4 times. So we sum this, and we take the we'll find the average of these numbers, and we'll try to put it in terms of n. So in this case, n is 1 2 3 to 5, and this average of this will be roughly 5. So in terms of n, 5 would be n over 2, and we are doing this on average on every element. We are doing n over 2 work. since the outer loop does n elements, the total time complexity will be n times n over 2, and we can drop the constants since we are only concerned about the upper bound, so this will be n square. I think I make it a little confusing. Is there any questions? Okay. So this is one other way to know if an algorithm is n square, if it's not purely n square, meaning if you are not going over there every time. And this algorithm is also in place since we are not using any extra memory. We're shifting the array on the inputs. We are not using extra memory, so it will be in place. So, and its stableness, yeah, it can be implemented to be stable. Because, for example, if there is for here, whenever the left element is equal to the current element we're seeing, we can choose to not shift this element. So in that case, you can make it stable. Yeah, and one thing about insertion sort is, it is in practice it is better than the previous n-square sorting algorithms because let's assume every element in an input is k positions away from its sorted position. So in that case, for every element on average we will only be shifting k times. So in that case, our time complexity will be k times n. So in practice, this will be faster than the other two n-square sorting algorithms. Yeah, this is all about insertion sort. Let me try to think if I forget anything. Yeah. Any questions?
Okay, if it's sorted, it's also
Yeah. So base case scenario for insertion sorted, if the given array is already sorted. In this case, we start from here. It is less than. We don't do anything. We do the same for 3. We do the same for 4. So it will be on n in base case scenario. Okay, let's move on to the next sorting algorithm. So this one is a little different from the previous algorithms because it's not comparison-based algorithm. We don't compare each element and do the sorting based on that. The way to do it in counting sort is to count every element, the appearance of every element in a separate array, and generate the sorted version of it using that count. To see it in an example. So let's let the input be this. Okay. So this is a given array, the given input. So to sort it in counting sort, what we are going to do is we will initialize an array to keep count of to keep the appearance of each element in the input. So to do that, we will find the maximum element here is 5, right? So we'll initialize an array of length 6 because we want to include the count of 5 also. 1, 2, 3, 4, 5. So the index of each the index will be 0, 1, 2, 3, 4, 5. And what this tells us is the count of 0 will be written here, and the count of 1 will keep the count of 1 here, or 2 here. So initially we go over the inputs. There is 4 initially, so we make the counter for 1. This means we have seen for 1 time, and we do the same for 1. For 1, we have seen 1 time, 2. We have seen 2 1 time, and again another 2. We have seen 2 times, 5. We have seen 5 1 time, and for 3 it's also 1. For 4, we have already seen 4 before, and now it will be 2. For 3, we have already seen 2 twos. For 2, we have already seen 2 twos, and now it will be 3. Yeah. So we created this count array. So from this, can you think of any way to build an output, the sorted version of the input?
We just iterate through this counter array list, and we will write 0 times, 1 times.
Yeah. So what he said is, we will iterate over this one. When the count of something is 0, we don't actually care, because we haven't seen the count of 0 is 0 here. That means we haven't seen 0 in the input. So what we do is, we have seen 1 time, so we put 1 in the output we are trying to build. We have seen 2 3 times. We put 3 2s. 3 1 time, 4 2 time, and 5 1. So we sorted the array in this way. Yeah, okay. Yes. So is this in place? Yeah, it's not in place. We used extra memory here, and also we can't always use counting sort, because here we created a count array of length maximum plus 1, right? So if the range of numbers is huge, we may run over the memory limits. So we can't always use it. We can't always use it. So whenever possible, I think it's a good option to consider counting sort. But be cautious about the range of the limits, the range of the numbers. Okay. Is there any questions? Yeah.
Is it stable?
Oh, sorry. Yeah. It can be implemented to be stable. We can actually see its stableness in a number, but we'll try to sort to use counting sort to sort objects. In that case, it will be clear. Yeah, it can be implemented to be stable. Any other question?
What about time complexity?
Oh. That is the most important part. I forgot about it. So the previous previous algorithms we have seen, their time complexity is n square. What about this one? Yeah, we only built an output a count array, only iterating the input once, and we also iterated on our count array once and build an output array. So can you? Okay, so let the length of the input be n, and let the length of our count array will be k. So our total time complexity will be big of n plus k, because we do the iteration separately. We first iterated over this one and built this one, and we iterated over this one and build our output array. So time complexity of counting sort would be n plus k. And whenever this is smaller than n, we can say it's no n, but to be sure, it will be n plus k. Yeah.
Given we iterate over the items first for the first time to find what's the maximum, so that we can allocate the maximum plus 1 in this case.
Yeah. It will be n iterations, right? So it will be 2n, but since we are only concerned about the upper bound, thank you.
Since the maximum value for k is n, assuming the worst state, won't that be to n and just assume n?
What?
Since the upper bound for k is n,
The upper bound for k
is n,
is it?
I mean, like, it will never be n, but
The upper one for k, you mean?
yeah.
Is it n?
No.
Yeah, because you can have a maximum of 100 here. So our count array would be the upper one. So any other questions? I've seen a hand around it. Okay. So let's see the visualization. So here it first counted the appearance of every element, like this one, and from there it will generate the output. Yeah. So here we do this approach if the input is a number, if we are sorting a number, but we can extend this this method. We can do a simple tweak on it and make it work for any object. For objects, for example, if we are sorting, let's say, a dessert object, which have type int price, and we are concerned, we are sorting the dessert object with price. So in that case, we do the same thing. We will find the maximum price and initialize our count array. Before we initialized it with zeros, right? Now we can initialize it with an empty arrays. So we can initialize our count array with an empty array, and we can iterate over the input. And what this means is, for every dessert which have a price of 0, it will be, we will put the object here, and for every dessert which have a price of 1, we'll keep it here. And after doing that, we will finally build the output, so the sorted version of the input, like we did in the previous slide. But be aware that we're not copying the object here, since we are only keeping the reference. Just it would be clear. Let's try it with this simple example. So we can see that counting sort is in place using this example. Let's say our input is, let's say we have a dessert of type A and its price is 2, and type B and price 3, type C and price 2, and type E and price 1. So in this case, the maximum price is 3, right? So we will initialize a count array with empty arrays of length is 3 plus 1, a maximum plus 1, because we want to keep count of keep the count of the maximum element. So we iterate over the input, and we see a dessert of type A with price 2. So we put this object here. I'm gonna write it downwards. So it would be A2, and we have gone to 3, B3. We will keep this 3 here. C2, since the price of dessert C is 2, we will keep it here. E1. So as we did before, we will iterate over this, and this is empty. We are not concerned with it because there is no desert with type price this. So here all of the objects with the specified key will be here. So we will iterate over this inner array and put them in their order. There is only one element in 1, so we move to 2. So we put all elements in this inner array into our output. E2 and C2, and do the same for C3. So, so to see it if it is in place, so in the input type P of type P desert of price 2 comes first of type C desert of price 2, right? So in the sorted version of it, it's in the correct order, so it's in place.
You mean it's stable?
Sorry, it's stable. Sorry, yeah. Time complexity will be the same. It's not in place. We use the extra memory. Yeah.
So, what if we had a price of 3 on all of the objects?
Yeah.
So wouldn't the time complexity be n squared because we would move all the objects on the last index, and then we'd have to iterate over them. So we'd have n squared. So wouldn't that increase the time complexity?
No, I think if all are 3, this all will be empty, and all elements would be here, right?
Yeah.
So okay. So time complexity of the algorithm is n plus k, right? So this will be of length k. Oh, yeah.
It's 2n.
Yeah, it's
It's n plus n.
what?
Populating is n,
Yeah.
and then printing it out is n, so it's n plus n. It's independent.
Yeah.
I will explain that.
Yes, since we have two separate for loops, not inside. That's why.
Any other question? Okay. So we don't have a visualization for this one, sorry. So here, these are the exercises. You implement all the algorithms, the sorting algorithms we have seen so far, and test them out on your own inputs. And after doing that, try to write a function that will generate a random number from 1 to 1000. That you have an array of 1 to 1000 in a correct way, but after you write a function to randomize that array. Yeah. After that, try counting sort for inputs that include negative numbers. Yeah. Any questions? Yeah. This is it for now.